All right, I guess I'll go ahead and start here because a lot of students are approaching me kind of worried about tomorrow's quiz. It's our first CFA quiz, which means we've got to give it through Eduphoria because some individuals at the home office would like to look at the results, the data from the quiz. So the good news is it's going to be multiple choice, but tomorrow's quiz is only about transformations. Okay, it is not directly connected to what we have here. Now, there's a quiz on Tuesday, which will be over limits and discontinuities, okay, in behavior, all that good stuff. And then a week from today, you have an open-ended quiz where you will actually be graphing one of these like we've been doing on the notes, like you've done on the homework, okay? But tomorrow's is just going to be transformations. So let me give you a few examples. Now, when I say transformations, I'm just referring to what you were taught in Algebra 2. Translations, dilations, reflections, things of that nature. Now, I did include some rational functions on there, but I also included a quadratic. I put a logarithm on there, basically just different graphs for you to describe the transformations. So why don't we start with log, because I'm looking around at the faces and I saw the biggest reaction when I said log. Okay, how many people remember logarithms? Okay, could confidently simplify or manipulate any expression that I were to give you. Okay, now not everybody's hand is going up, and that's fine. Now see, tomorrow you don't have to understand exactly what a log is. It's more about the transformations. You're just applying those to some parent. So let's say we have, let's use the common log. That would be base what? 10, okay. So let's say I were to give you something like, oh, how about 3x plus 9 minus 2? Okay. So it doesn't matter what the log parent looks like. You simply have to describe the transformations that have occurred to the original. Okay, now I'll go ahead and tell you there are 3. Who can tell me one? Okay, Andrew, what do you think? Okay, there's a vertical shift down 2 units. Yeah. Okay. Vertical shift down. And I won't go ahead and write 2 units. Okay, it's down because you're subtracting. Okay, 2 more. Is That's exactly right. When you're thinking about the x's, remember they are always different. That's all. Oh, you're going to do the third one? Oh, okay. So I just wanted to go ahead and point out, we've already seen if you're adding and subtracting to x directly, you take the opposite. If you're multiplying by x, you take the reciprocal. So this one here, yes, that is a horizontal compression, or should be compression by a factor of 1/3. The reciprocal is the true scale factor when you're multiplying. Okay, and that's how you can also tell the difference between your transformations. If you're adding or subtracting, it's got to be a translation. If you're multiplying, has to be a dilation. What's the one item that gives me a reflection? The negative. That's the negative's one job. Okay, is to reflect. Now, depending on where you place him, you could reflect with the x-axis. You could reflect with the y-axis. Okay, there's one left. Natalia? Okay, left 3. Now, you're correct. We are going to go left because we take the opposite. But you said left 3, but that says 9. There's another rule that people forget. Was there anybody who was thinking you have to shift left 9 units? How many people were thinking that they just don't want to raise their hand? Ah, see, I almost got you. Okay. It's true. You can't look at the horizontal shift until the coefficient of x is 1. You have to factor out that scale factor. So I could rewrite this as log 3x plus 3. See, you still have the same dilation, but now we know the whole graph is going to shift left 3 units. That's what tomorrow's quiz is. Okay, we've mentioned, this on and off throughout the lessons because transformations have come up, but it's not something that I'm talking about directly because you were already taught that in Algebra 2. So remember, if you're having some issues, if you're not remembering, okay, if you go to the pre-cal website, now that's next week. If you go to this current week, I've got that document I uploaded that walks you through several examples. Okay, that is still available. And I'm here in the morning if you need help. Okay, now what's nice about this, I don't even have to give you a function. I could go ahead and use function notation. Okay, so what if I gave you something like 1/2 f of 5x plus 3? I can apply that to any parent function I want. It doesn't matter. What's important is I just see the transformations. Who can tell me one? Okay, Fernando? There you go. I know the entire graph, whatever it looks like, is going to be shifted 3 units up. Perfect. Connor. Horizontal compression. There we go. Okay, that is a horizontal compression. So the 2 examples I gave you were horizontal shrinks. What if I wanted to stretch it horizontally? What kind of coefficient would I have to put in there? Yeah, it'd have to be some kind of fractional or decimal value. Like if I put 1/4 in there, then it would be a horizontal stretch or expansion by factor 4. Okay, and that's all. A vertical compression by a factor of 1/2. That's what the quiz is tomorrow. Okay, just the transformations. Does everybody feel a little better about that? Okay, so don't worry, Mr. West has a plan. I've always got a plan. May not be a good plan, but it's always a plan. Okay, so we'll take care of that tomorrow. I mentioned on Tuesday we're going to have another CFA quiz. I wanted to go ahead and just get them out of the way because we have to have minimum at least 2. As long as we do 2, we're okay. So I'm going to go ahead and get the 2 out of the way, and then we won't have to worry about it again until the next 6 weeks. It's horrible to say, but it's the truth. Then next Thursday, that's where we go back to the normal quizzes, what we were doing on the notes. Okay, that one is not multiple choice. You will go ahead and graph for me without a calculator. So with that in mind, what would you guys rather do? Would you rather spend your time looking at questions on the assignment, or do you want to go back to the notes? The assignment, okay. Do we have a question? Number 3, okay. Let's take a look. Now, several people have already approached me about numbers 3 and 4, and they got confused because it says describe the transformations of the reciprocal function g of x equals 1 over x. So some people were asking me, well, do I just put x plus 3 over x minus 2? What word were they focused on? The reciprocal. But this here, this is the rational parent. This is the guy that started it all. All the graphs that we've been looking at, they originate from this guy right here. Well, besides calling him the rational parent, we can also call him the reciprocal function. So we're not saying take the reciprocal, we're just saying that's the name of the function. Does that make sense? Okay. Whoa, that was weird. Okay. So basically, what we're told is we're starting with the rational parent, this guy 1 over x. Well, this is the new transformation. Okay, so you want to describe the transformations that you see, basically just like we were doing a moment ago. Now, what I'm about to show you, you have to get kind of creative, and you can really only do this if you have a linear function divided by another linear. What I want to do is write it in this form. I want to have it as a plus b over x plus c. If I can get my rational function in that form, I'm going to be able to list the transformations like we were doing a moment ago. Can anybody tell me, what do you think a represents? What kind of transformation? That's a vertical. Oh, it's not multiplied, it's what? It's added, so it's a shift. So A would represent a vertical shift. What's B? Now, B would be your dilation. Okay? Because when you have a fraction, there's all kinds of things you can do with fractions. If I have the expression just B over x plus C, is that equivalent to B times 1 over x plus C? Yes. So that's why B is the dilation. So typically anything in the numerator is going to stretch or shrink it vertically. Okay. And one thing you're going to find if you really start analyzing transformations, you can have it change vertically but affect it horizontally and vice versa. Okay. If you want a vertical change, you don't necessarily have to place it where a vertical change would normally be. Okay, and I'm not going to get into that right now. Now, what do you think C would be? That's the what? That's the horizontal shift. Okay, so if we can get it in that form, we're good to go. All right, well, let's go ahead and take a look. I've got to somehow rewrite this expression so that I can get one constant plus the fraction. So like I said, I'm going to get a little creative. I'm going to rewrite x minus 2. Up top, I'm going to say x plus 3, and then I'm going to say minus 5 over x plus 3. Okay. And there's some people looking at that going, what the hell? Okay, all right. How am I correct? There you go. But is it equivalent? What's 3 minus 5? It is negative 2, so it's equivalent, right? Okay, well, here's why I did this. If you're going to add or subtract fractions, you have to have a common what? Common denominator. Now, that rule, like a lot in mathematics, they're reversible. So if I were to have something like, a plus b over c, I can say that's a over c plus b over c. Okay? That's still very acceptable. So I'm going to do that here. I'm going to pretend that one of my terms is that group. That's one numerator. Minus 5 would be the other numerator. So I'm going to go ahead and say x minus 3, or excuse me, x plus 3, okay, over the x plus 3, plus negative 5 over the x plus 3. So what's anything divided by itself? 1. So this is 1 plus negative 5 over x plus 3. See, now I have that form I was describing to you. I can look directly at it and identify the transformations. Do you guys remember that form? The a plus b over x plus c? Were you guys shown that in Algebra 2? No? Doesn't make sense. Okay, there we go. All right, so what we just did a moment ago when I gave you the log, when I gave you the f of x, tell me what transformations you see here. Okay, now that's actually 2 transformations. Remember, the negative's one job is to what? Reflect it. So where you place the negative, this would be a reflection with respect to the x-axis. Okay? So where you place that negative is very important. If the x itself is negative, then you reflect it with what? The y-axis. Okay? So we know we have a reflection. Now, putting the negative aside, what were you saying about that 5, Connor? Dilation. It's dilation. Now, vertical or horizontal? Vertical. It's not directly connected to x, so it's not horizontal. Is it a stretch or a shrink? Okay. Or, mathematically, we would say vertical expansion by factor 5. Vertical expansion by factor 5. Like, even I sometimes just go back into shrink and stretch. Okay. Again, you guys have taken a district assessment before, right? You remember those style problems? Okay. That's exactly the type of questions that you're going to be getting on these quizzes. They're multiple choice. Okay, so don't worry about it. It is for a grade. I mean, you want to do your best, but, okay, don't sweat it. Okay, what else? There's 2 left. Vertical shift where? Okay, so vertical shift, or translation, okay, whatever you want to say, up 1 unit. And there's 1 left. Okay, because that's directly connected to x. So horizontal shift left 3 units. Boom. That's what it wanted you to do on numbers 3 and 4. Now, it also wanted you to go ahead and do some analysis. Like, if I were to look at the original problem, this guy right here, okay, what's my vertical asymptote? -3. So it wanted you to go ahead, the limit as x approaches -3 from the left, and the limit as x approaches -3 from the right. Okay. Philip, did you want me to do that as well, or was it just the transformations? Does do that as well? Okay. Now, let's go ahead and kind of get a quick sketch here. I'm not going to worry about sketching the whole thing, but is everybody okay why we have a vertical asymptote at -3? Why is -3 not a whole? It doesn't cancel. Only if a term or a group factor cancels will it be a whole. Okay, so -3. Okay, so x equals -3. Now remember, my suggestion, this is how I was taught way back in the day, and I'm going to instruct you guys the same way. If I'm going to analyze the behavior on either side of a vertical asymptote, I choose a value 1/10 of a point on either side. So what's 1/10 above -3? Okay, so that would be -2.9, right? Remember, because that's larger than -3. What would be on the left? -3.1. Okay, well, you'll notice I've got one group above and I've got one group below. I'm just going to mimic what I see. Remember, this is the time I'm only interested in the signs. Okay, if I were to take -3.1 and plug it in, what's -3.1 minus 2? That's a negative. Again, does not matter to me what the value is. I'm only concerned with positive or negative. What about -3.1 plus 3? Okay, that's a negative. So a negative divided by a negative, positive. So I know as I approach -3 from the left, this guy wants to curve up. Okay, that's my analysis. That's how I can kind of determine what the graphs are going to look like. All right. Now, is it guaranteed that the other side is going to be going down because this side was up? Okay. It's not a guarantee. It's probably a good bet, but it is possible for both sides to go to positive or negative infinity. So I always encourage you to look. So we took care of the -3.1. Well, now let's just do the same thing with the right side. Okay, -2.9. So what's -2.9 minus 2? That's another negative. -2.9 plus 3. That's a positive. So where's this guy going? He is going down to negative infinity. Now remember, that limit analysis, I'm only going to require that you do it if you need to. If you feel you have enough information that you can confidently draw your branches, please feel free to do so. But if you want to double check yourself, you can use that limit analysis. That's what we're talking about here. Okay, Philip? Is that good? Okay, did anybody else think that about number 3? No? Okay. Anya, what else you want to talk about? Number 4, you want to do the same thing. Okay. Now, I could go ahead and use a trick similar to what I did on number 3, but number 4 is actually a lot easier than it looks. Do you notice anything about him? There you go. This guy can factor. So I've got x minus 3 over x plus 3, x minus 3. What do we call those groups? Where the first terms are identical, but the second terms are opposites? Starts with a C. Was it? Not corresponding. That deals like a transversal. Conjugates. Remember the term conjugates? Okay. Well, those cancel. So all I have left is 1 over x plus 3. But see, just by factoring it, I didn't have to do anything special. I've got that version that I was looking for. In fact, what's the only transformation that's happening here? He wants to shift left 3 units. Okay, that's it. Did you need me to finish up that problem, or? Okay. Now this guy does have a what? He has a hole because we had a group that canceled. The hole would occur at 3 because 3 minus 3 is 0. Okay, good. Good questions. What else? Hey, Fernando. 10. 10's been a popular one today. Okay. Let me show you number 10. Okay, so x cubed minus 1, x minus 1. So these last problems here, this is exactly what we've been doing the past couple of days. We're just graphing rational functions. Now, on your notes, most of them were already factored, so we can just get right into the problem. But these, like your quiz next week, you got to factor before you can get that ball rolling. What part of this can I factor? The top. Okay, this is a difference of cubes. Okay, so a cubed minus b cubed. Now you might recall that when you factor a difference of cubes, you're going to end up with a binomial times a trinomial. Okay, it always is going to have that form. Does anybody remember an acronym that you may have been taught? So, what are you talking about when you say so? Same, opposite, always positive. Well, we're talking about the sign. So I'm going to use the same sign, the opposite sign, and then always positive. Okay, well, we're taking a cube root, so we're looking at our terms a and b. Well, the first one would simply be just a minus b. Very quick binomial. Does anybody remember what we do in the trinomial? A squared plus a times b plus b squared. There we go. That's the version, factored version we want to get. Now, in this case, a cubed equals x cubed. So what's the cube root of x cubed? X. So everywhere I have an a, I'm going to replace it with x. What's the cube root of 1? 1. So everywhere I have a b, I'm just going to replace it with 1. That's the nice thing about sum and difference of cubes. If you remember the, don't want to call it a formula, but if you remember the form, it's just substitution. Okay. So this guy would be a minus b, so x minus 1, times, if I square x, that would be x squared, plus x times 1, plus 1 squared. Now this is all over x minus 1. Okay. Now, did we notice anything? We can cancel, but this problem actually turned out to be like the first problem we did yesterday. You remember where we started off thinking it was irrational, but after the cancellation it became linear? This is the exact same type of problem, only this guy's not going to be linear. After I cancel, we're graphing that quadratic. Okay. So let's go ahead and start with the whole. Where does the whole occur? At what value of x? 1. Okay. So is everybody okay with that? No questions? And while I'm thinking about it, the quiz on Tuesday, where we start talking about limits and discontinuities, what mathematical term could I use instead of whole? What kind of discontinuity? Does anybody remember? Starts with R. Okay, removable discontinuity. All right, so if you see removable discontinuity, that's the fancy way of saying whole. Does anybody know what we call a vertical asymptote? What kind of discontinuity? Okay, it's an infinite discontinuity. All right, so don't let the vocabulary stump you. Okay, infinite discontinuity, vertical asymptote. Removable discontinuity, whole. There we go. Okay, so how do I figure out the y value of the whole? Yeah, take that x that I found and just plug it into every remaining x. So 1 squared plus 1 plus 1, that's x squared plus x plus 1. Well, that's just 3. Okay, so it looks like our whole occurs at 1, 3. All right. And then all we have to do now, I mean, there's no asymptotes here. I mean, it's going to turn out there's no intercepts. We don't have to do the same steps that we were doing for rational because it's not a rational any longer. It's a quadratic. So I would probably just go ahead and graph him like you would graph any other quadratic. Personally, I would start with the vertex. Does anybody remember a little expression involving a and b that would find me the x value of a quadratic's vertex? You are the only person today to remember that so far. Fantastic. Give her a round of applause. There you go. Presumpsa. Amazing. Good. The opposite of b over 2a. Do you guys remember that expression? That will also give you the equation of your axis of symmetry. Okay. So let's see here. B is 1. So the opposite is negative 1. 2 times a, 2 times 1, 2. Well, there we go. Looks like the vertex occurs at negative 1/2. Okay. So how do I figure out what the y value is? What am I going to do with that negative 1/2? Just plug it back in. In fact, you guys might remember this. You may have seen this notation in Algebra 2. The vertex is commonly described as this. Do you guys ever remember seeing that before? Remember, this is your x value, and then we're telling you to put that x value in the function. Because f of x is what? Remember, that's your y. Nobody remembers seeing it like that? Really? Okay, well, that may be something I would go ahead and copy down, because you're going to notice this is pre-calculus, and we're going to start getting into trigonometry, which is going to dominate what we're going to do throughout the year. But really, how much Algebra 2 has been coming up? A lot. It's going to come up a lot. We need those skills in order to be able to continue with what we're going to be looking at. So don't worry. We're going to take it a step at a time. Math is fun. Okay. All right, so let's plug it in. So x squared, that would be a negative 1/2 squared plus x. So I'll just go ahead and say minus 1/2, and then plus 1. Okay, so let's simplify it. Negative 1/2 squared. 1/4. Minus 1/2 plus 1. Okay. Now we do need a common denominator. So that would be 1/4 minus 2/4, because that's 1/2, right? Plus 4/4. I just made sure I'm dividing by 4, because 4 divided by 4 is 1. 2 over 4, 1/2. We're good? So what's that become? 3/4. Okay. So the vertex should be happening at negative 1/2, 3/4. So maybe right about here. Okay. So it's definitely not touching the x-axis. If I were to solve this guy for his roots, what would I get? I get imaginary. Okay. Somehow, some way it'd be imaginary. Now, that's as much work as I would probably put into the problem. You could go ahead and choose different values of x and plot the points, but I would just use his symmetry now. In fact, I know this guy opens up. I would take this hole and just reflect it over. So it looks like horizontally he's 1.5 units away. So 1.5, put him on the same level. So you're probably looking at something like this. Okay. And then I'll make sure to label that hole. Okay. Fernando, is that good? Okay. Questions? Anybody confused by anything I did? Not sure where I got a value from. Okay. All right, what else? That's it? No more questions? We should just do all of them? Oh, in an ideal world, fortunately, our time is limited. So, Jordan, do you have another one that you think is the most important? Oh, you didn't even look at it? At least you're honest. There you go.
I'll throw a number at you. Number 14.
14. Okay, let's take a look. Okay. Now, we probably don't have time to go ahead and run through the entire thing, but I think that probably the most important thing here may just be the factoring. If you can get past the factoring, then we know the steps. Like if I want the x-intercepts, what would I set equal to 0? Starts with an N. The numerator. If I want the vertical asymptotes and or the holes, what would I set equal to 0? The denominator. Okay. I can look at this guy without doing any work, can tell me the y-intercept. Who else can do that? Okay. Kashal, what is it? There you go. Remember, what's the shortcut for finding the y-intercept? Divide the constants. Because if all these x's just become 0 and they disappear, all you have left are your constants. Okay. Caleb, can you tell me where the horizontal asymptote is just by looking at it? Y equals what? Well, that's the equation of a horizontal line. So y equals, what's the value of the horizontal asymptote? Okay, don't know. Jake, can you help him out? Oh, you're killing me. Sir, it is 3. Where'd you get that? There you go. Now, how'd you know to divide those first 2 numbers? Look at the powers. Remember the degrees. The second page of your notes had those 3 cases for comparing the degrees. If they're the same, divide the leading coefficients. What if the numerator is larger? Then there's a slant. typically a slant. Could be something else, but you'll use long division or synthetic. Okay. What if the denominator's degree is larger? Then it's just 0, the x-axis. Okay. All right, so let's take a look at this. Now, again, you can have any method you like. In order to factor these trinomials, what do I like to use? You like my impersonation? Because this is how you drive, right? If you want to crash into a tree, yeah. It's a joke. You'll laugh later. Okay. So I'm going to go ahead and run through that. If you have a method you prefer, please go ahead and use it. We're going to be using this again tomorrow on the next focus activity. But let's say I want to factor this numerator. The first thing, m in my, stands for multiply. You multiply the leading coefficient by the constant. So 6 times negative 6? Negative 36. Now, the only way to get a negative product is one negative, one positive factor. Okay? This is the key to the entire process. I need two numbers, two factors, that will multiply to give me negative 36, but they have to add to give me what? Negative 5. It's got to give me the middle term. What are we thinking? Oh, now, 6 and 1 would work, but what's 6 times 1? We need factors of 36. So Natalia says 9 and 4. Does it matter which one's positive, which one's negative? It would have to be negative 9, positive 4. Okay. So I've multiplied. I found the two factors. What does the D stand for? I'm going to divide. Well, you always divide by the leading coefficient. So here I'm going to divide by 6. What's the R? Reduce. We're going to simplify. So negative 3/2. 4/6 becomes 2/3. Now the second M tells you to move those numbers to create your group factors. Now that first fraction, negative 3/2, would that be negative 3x plus 2, 2x minus 3? 2x minus 3. You always start in the denominator and work your way up. So this would be 2x minus 3. The other one would be 3x plus 2. Okay. All right, that first one's done. Now, I want to go ahead and take a look at the denominator. 2x squared minus 7x plus 6. First step, multiply the leading coefficient by your constant. What do I get? 12. Now, there's two ways to multiply and get a positive. Either I'm looking for two positive factors or I'm looking for two negative. What do you think? Why two negative? There you go. The clue is in the middle. I need a negative sum. So are there any two factors of 12 that'll work here? 4 and 3. Negative 4, negative 3. What will I divide by? 2. Okay. So let's see here. Negative 3/2 will stay the same. Now, if it does become an integer, if it simplifies nicely, you just want to make sure to leave it as a fraction. We definitely want to still leave it as negative, but leave it as a fraction. Remember, we need both the numerator and denominator to create the groups. So what is negative 2 over 1 going to create? X minus 2, negative 3/2, 2x minus 3. There you go. And you see how it went faster? Once you know the steps and you know what exactly you're doing, it only takes seconds to factor a trinomial. Now, I'm always going to promote that method. I like it. Okay. How many people in here think they'll use it? Wow, that's actually a lot of hands. Good, good. Like I said, don't feel obligated to do it. If you have another method, please feel free. Okay. Now, do you notice anything about this guy? 2x minus 3s, they cancel. So this guy has a what? He has a hole. Now, let's go ahead and find the hole because this one's actually a little different than any other one we've seen so far. Okay. The group that canceled, that's going to tell me where the hole occurs. So 2x minus 3 is equal to 0. So if I add the 3, divide by 2, what am I looking at? 3/2, right? Now, if you want to keep it 1.5, that's perfectly fine. I'm going to go ahead and stick with the fraction. Now, I know it occurs at 3/2. How do I go ahead and get the y? We plug it in. The only difference here is that now there are several places on different levels where I'm going to plug that in. It doesn't change anything. So 3x plus 2 becomes 3. times 3 halves plus 2 over x minus 2, 3 halves minus 2. Okay, so now I just need to simplify the whole thing. Okay. So let's see, what's 3 times 3 halves? That's 9 halves. Okay. Or 4.5 if you're sticking with the decimals. Okay. 9 halves. So let me go ahead and rewrite this. It would be 9 halves plus 4 halves over 3 halves minus, again, 4 halves. Okay. Because we always need a common denominator. So what do I have up top? 13 halves divided by, okay, that'd be a negative 1 half. Okay. Now what happens if you're dividing by a fraction? You multiply by what? The reciprocal. So this would be 13 halves times negative 2 over 1. Those 2's are going to cancel, so it looks like that guy occurs at negative 13. So this is one of the examples where that grid is not quite adequate, so it's not too far off. So when we have 1.5, maybe 11, 12, 13, maybe about right there. So it's going to be a little ways off your grid, unless you count by 2's, okay, if you want to do that. All right. But I think that's as far as I'm going to go on that particular problem, just for the sake of time, because I do want to take a look at that paper you picked up when we came in. Because this is essentially what your Tuesday quiz is going to be over, limits and discontinuities. Okay, so I put this together for you. Just some more practice to hopefully make you feel more comfortable with it. This has already been graphed for you. We've got the function there. We're told the whole occurs at 3/7. Now, this is just verbalizing the same thing we've been doing in class. Okay, so when it says, as x approaches negative infinity, the graph of f of x approaches, well, this is no different than saying the limit as x approaches negative infinity. Now, you can go ahead and put the name of the function following that, okay? Or you can put the actual equation itself. You'll see a lot of other people go ahead and do that, but it's the same thing. It's the same idea, just worded this time. Does that make sense? Okay. Now, what do we call this? If you're approaching negative or positive infinity, it was 2 words, started with an E. That's end behavior. When x approaches positive or negative infinity, that's end behavior, right? When you have end behavior, what do you really want to look at for the graph? The horizontal asymptote. Okay, so it does not matter if one branch approaches from above or if another branch approaches from below. Okay, as x goes to positive or negative infinity, what's the y value of the graph going to approach? 2. Where'd you get 2 from? Yeah, because isn't the horizontal asymptote y equals 2? Okay. Now, we're going to go ahead and skip these next ones for just a moment. Those are kind of unique. We'll come back to those. Now, as we approach negative 2, well, what's negative 2? Ooh, that's a vertical asymptote. What's the mathematical term? What kind of discontinuity? That's an infinite discontinuity, okay? So as we analyze the side behavior of a vertical asymptote from the left and the right, remember, there are only 2 possible answers here. What are they? It's either positive or negative infinity. So here is negative 2. Okay. If I approach it from the left, well, what's the graph doing? He's curving up. So what should I put here? Positive infinity. Okay. What's he doing on the right side? Is he curving up or curving down? He's deciding to curve down, so that's going to be negative infinity. Okay. It really is just that easy. Now, don't get me wrong, limits can get way more complicated than this. When you get to calculus, that is something you're going to be spending quite a bit of time on with Mr. Heinrich. Okay. My job is just to introduce it to you. Okay. Now, let's go back to 3. Do you notice anything? What is 3? It's the whole. Okay, what's the mathematical term? What kind of discontinuity? That's the removable discontinuity. Remember, those are the two we want to remember, infinite and removable, whole and vertical asymptote. Okay, well, as we approach 3 from the left and the right, what is the function y approaching? Well, let's see. If I'm approaching 3 from the left, so let's say 2, 2.5, 2.9, 2.999. As I get closer and closer to 3 from the left, what is the y value approaching? Anybody think they know? It is 7/5. Now, some people are saying, whoa, 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 that point doesn't even exist. Okay? And that doesn't matter. The function may not be defined at that location, but the limit exists. As you get closer to 3, these y values should be getting close to 7/5, whatever that decimal is. Okay, what was it? 1.2, whatever it is. Okay. So what do you think if it's approaching it from the right? Still 7/5. Okay. All right, so the function is undefined there, but the limit, as you approach the value from both sides, does exist. Okay, it's very easily confused. Okay, well, now all we have left is domain and range. And remember, everything we've talked about here is going to apply to the graph below. Okay, so now, walk me through the domain. This guy is definitely infinitely wide. Okay, but I'm coming in from the left. Is there any kind of obstacle that I hit? What's the first thing I run into? First thing I hit, I got a problem with this asymptote. So I'm coming in from negative infinity, and I have to stop at that asymptote. Okay? Because this first branch ends there. But where does the other branch begin? I can start him at the exact same value. Again, as long as I'm not including that value. That allows me to get infinitely close. Now, I'm traveling along again. Is there anything in my way, or can I go all the way to infinity? Natalia said 3. What's wrong with 3? That's where we have a hole. That value of x has been removed as well. So I'm going to say to 3, union 3 to infinity. See, as I'm traveling through, there are only 2 times where I run into obstacles. It's the vertical asymptote and then the hole. But you'll notice he's still going from negative to positive infinity. I'm just telling anybody who looks at my work that negative 2 and 3, we got to throw those out. Now, vertically, you're going to be doing the exact same thing. It will go from negative to positive infinity, but what you have to ask is, what values of y, if any, do I have to remove? Okay, so take about 30 seconds, write down what you think the range of this function is going to be. Interval notation. Okay. So by show of hands, who thinks they've got it? Okay. Let's see, who haven't I talked to today? Clarissa? What would you tell me the ranges? Okay. Union. Is she right? That is perfect. That is perfect. Now, vertically, you know, there's a very, very thin area, but the graph does exist between 7/5 and 2. She had to remove those because 7/5 is the y value from the hole, and 2 is the what? That's the horizontal asymptote. So you're going to run into that when you're looking vertically. How many people had that right? Nice. Observation, I'm noticing that there's way more hands going up now than when I said how many people think they got it. Maybe I should just ask how many people have an answer, but they're not 100% confident in it. Okay, got to be confident, got to be confident. You're going to be wrong sometimes, and that's okay. You're probably thinking to myself, well, Mr. West, you've never been wrong. It's way too quiet in here. Okay. Okay. Well, there we go. Looks like we got less than 2 minutes. Are there any questions? Are we starting to feel a little more comfortable with this material? Sandra, you're shaking your head no? Is there something I can do to help?
Not sure.
You're not sure? Okay. I am here.